We look at the general Riemannian geometric context, saying does every smooth manifold of dimension bigger than or equal to 3 admit a metric with a negative scalar or rich curvature? So this question is somewhat related to topology and geometry relation context. So we know that easily we can easily construct a negative scalar curvature Riemannian metric on any smooth manifold. So I need to explain this one a little. So any smooth Riemannian manifold, if you enlarge it by multiplying by b constant, then the small neighborhood looks like it's close to Euclidean space. So in this context, we look at we divide to two steps. So we construct a metric on this small neighborhood. So this small neighborhood is close to a Euclidean space. So just assume that it is Euclidean space, and you can get a metric with a negative scalar curvature on a closed wall. And then, step 2, we expand this negative scalar curvature to all over M by conformal change. So this conformal change, the deformation formula is simple. So if you have a very negative scalar curvature on one space, just on one place, if it is very negative, then you can extend to all over M. So this should be clear. So that's step 1, step 2. But and then people studied the rich curvature, and it was pretty long studied. And then by Lockham in 1994, it was proved for rich curvature. And for rich curvature, if you look at the proof, then it's very much more complicated than scalar curvature case. So just a step here. When we deal with a scalar curvature, then you just look at only one spot, one neighborhood of a point. But here, when you deal with a rich curvature, then you have to deal with many points on the manifold. And then he did a smart controlled expansion of this negativity of curvature, and he succeeded. So, so the motivation for above question was to find the relation with the topology and the curvature. So now we look at the, so here the title only talks about contact manifolds, but for me, contact manifolds and symplectic manifolds are pretty related to each other. And from my point of view, symplectic points came first, and I studied that, and then I'm trying to extend it to contact manifolds. That's the one thing. And another thing is the symplectic manifold was slightly simpler than contact manifold. So I'm going to talk symplectic manifolds together. So anyway, extensive study was done for symplectic and the contact manifolds recently. And is there Riemannian geometry on them? Well, we know the answer. And we are interested in relationship with such geometry with the symplectic or contact topology. So we do know the almost scalar and the contact metric geometry from long time. So first, I just mentioned the almost scalar and contact. Many of you already know this one, but I guess I have to explain what it is. So on a symplectic manifold, almost scalar metric is a Riemann metric with this relation. Here, J is an almost complex structure. So if J is integrable furthermore, then it is almost scalar. So any scalar metric is almost scalar. And there are lots and lots of almost scalar metrics compatible with our symplectic structure. So a single metric Well, it may contain topological information, of course, but I'm going to just point out that it may not also, it may or may not contain topological information. But now here, we are thinking of the space of all almost scalar matrix versus to symplectic topology. So we have asked just similarly as the general Riemannian context, does every symplectic manifold of dimension bigger than or equal to 4 admit an almost scalar metric with a negative scalar curvature? So if you cannot, if you find some symplectic manifold which cannot admit such thing, then there must be some symplectic topological obstruction. And but the answer was yes. And yeah, I myself proved this one for published last year. So question is now we here in this talk I'm going to ask the similar question to contact case. Does every contact manifold of dimension bigger than 3 admit the contact metric with a negative scalar curvature? So the quick definition on a other dimensional manifold, a contact form is one form eta, satisfying this sort of they call non-degeneracy condition. Eta then determines the vector field xi by these two equations. So on a contact manifold, a contact matrix is a Riemannian matrix such that you have one equation and the second equation. Here, so if you recall the almost scalar matrix, then that was similar to this one. At that time, phi, you replace phi with j, then g, j, then you had omega here. So this looks more complicated, but actually, if to understand this one quickly, if you, so here, okay, first phi is field of endomorphisms of tangent space satisfying this one. So still this is, you may think it's complicated if you look at this one for the first time. But one way to understand this one quickly is that if you ignore this eta part, then it's a phi square equals minus identity. So it's almost a complex structure. And if you put it here, as I told you, ignore eta for a moment, then this is almost a Hermitian condition. And then this is, if you think of d eta as omega, as you have seen, then this looks really almost a scalar matrix. So at first glance, this almost contact matrix seems related to almost a scalar metric. So yes, a contact metric is closely related to almost scalar metric. So one instance to show this close relationship is such a thing. If M eta, this contact structure is regular, what they mean is the integral curves of xi induce an S1 bundle structure. Okay, then we can define a simplex structure on B. That's a so-called Wang theorem. Supposed to be Wang or Wang theorem. Then, okay, thank you. Yeah, then a contact metric can induce an almost scalar metric on B each other, roughly speaking. And so it seems not hard to show that every regular contact manifold of dimension bigger than equal to 5 admit a contact metric with a negative scalar curvature. Why? Because the base manifold is now 4-dimensional and it has almost scalar metric on it. Then there exists the result of almost scalar metric with a negative scalar curvature on B. I just mentioned that, right? So on the base you have a negative scalar curvature manifold, and then you have a S1 bundle. In this Riemannian submersion context, you can easily, without much problem, you can easily get a negative scalar curvature contact metric on it. So then, how to attack general contact manifolds? In other words, I want to remove this. I want to ask if we can remove this regular condition. How to attack general? then every contact manifold is locally regular. Locally, everything is good. So locally, there exists the contact metric with a negative scalar curvature. Then, yeah, you can easily get it. But this local data does not give a global data for Riemannian matrix, right? So this theorem seems to have something. Every contact manifold of dimension bigger than equal to 5 admits a contact metric with negative scalar curvature. I could remove this regular condition and arrive at this general context. So how to understand this, how to prove this one. So before I get into the proof, let's just think over this theorem. First, does this statement sound that this theorem sounds to be true or not? That's the first question. And the second question, well, you can ask if this is interesting or not. But first, well, I'll point out one the essential thing in it. So when you think of almost calorimetric, so fix this symplectic structure, and you think of the compatible metric, compatible almost calorimetric with respect to eta, omega. Then you know that there are a lot. How many? Well, actually there are well, of course there are infinitely many dimensional deformations possible, but if I say if I call the degree of freedom, then actually at least you can put more than one functions into it. At least one. So let's say 2. Actually, there are more than. If you can put you have 2 functions, free functions, and you can put these 2 functions into scalar curvature formula, then you have a chance to make it negative. That's what I learned from this almost scalar computation and also in this computation. But that gives why this becomes true. So let's recall that. Let's recall the two. Recall means the. Oh, sorry. Recall means we think of the general Riemannian context. I mentioned the step 1, step 2, right? So step 1, what we did on Euclidean space, we construct a metric with a negative scalar curvature on a closed ball, and then we expanded it. So we are still thinking of these 1, 2 steps. So first, we look for a metric G on RK called the negative curvature model, such that its scalar curvature is negative inside the ball, and it's close to the Euclidean metric away from B. So the graphical representation is this one. So so this horizontally is a manifold. Sorry, RK. Sorry, this is RK. Inside you have a ball. On this ball, this is the graph of scalar curvature. So the red one means negative scalar curvature, and this level, this height is 0. So it's a. I didn't say it's a. I didn't say it is Euclidean, but it's close to Euclidean. So it's almost. But it's almost scalar curvature is almost 0 here. Actually, it's very close to the Euclidean metric in any C infinite CK sense. So you have a Euclidean metric inside, but you have a negative scalar curvature inside. So if you look at this picture from above, then I have this shape. On a ball, you have a red negative scalar curvature. Outside, you have a Euclidean metric. So that's the negative curvature model. And then then I'm going to deform this above metric. So above metric was this red color at first, right? At first, but now I'm going to move. I'm going to deform. I'm spreading or expanding negative scalar curvature. which was concentrated in here, but I'm going to moving out, spreading out. But in compensation, I will lose negative scalar curvature inside. So that's the local stuff. So we'll look at the global manifold. So global manifold, maybe this manifold, at first I'm enlarging quite much. So then this whole thing, everything, the whole thing is the M, the enlarged manifold. But I only put these red balls only on this small area. But you can assume that there are all over the red balls here. So I put since I enlarged much, so this white color means it's close to Euclidean. So you can plug in. We got the negative model, and then we can put in here. It doesn't cost much because it was close to Euclidean, and then the negative model had close to Euclidean outside the ball, so it doesn't cost much. You can put it here, right? So when I will put in a uniform way, which I will explain again. And then the idea is, then what I'm thinking is I'm expanding all this way. By the way, I forgot to mention important thing. So the scheme of this proof is actually quite complicated, and it's not mine, but it's done at first by Rokamp. He did it in general Riemannian context to get the negative ridge curvature, and I'm doing for scalar curvature in a strict class. If I extend it in this way, so this scalar curvature was on here, but this yellow color is the spreaded part. The red negativity was spreaded all over up to here, and then it can cover all over, and then you may get the negativity on M. But this expansion is quite complicated, and it cannot be done it's nothing we can easily speak, actually. So we again look at this the same shape, and then and then divide these balls into finite number of classes. So I put number. Oops, do you see the number 1, 2, 3, right? So number 1 is here, here, here. 2 is here and here. So the same number of balls should be spread far from each other if they are same number. If they are a different number, like 1 and 2, they can be relatively close to each other. Okay, that should be arranged first, and then expand only number 1 balls first, and then number 2 balls, and then number 3 balls and number 4 balls, and so on. And then this way is a little better than doing at once, doing everything at once. But still, there should be some. So from number 1, so you think from number 1, when I expand the number 1 balls, it was no problem because it's just a simple expansion. When you do number 2 balls, the complication may come because number 1 balls shook something, and then it's not so the previously done area may have been affected a little too much. So simple expansion of number 2 balls may not do something about it. So there may some such complication may occur in the common region. Yeah. So yeah, how to avoid such a thing? is the key. So if you can, so from one ball to number 2 balls, and then you do number 3 balls. So for it is, let's say if you are done with the the k step, okay, and then you have to do k plus 1 steps. And if you can do just this one step, then that's general, and you will be fine, right? So how do you get from one step to next step without complication? That's the core of the argument. So before I get into that issue, I will make it something a little specific here. So here I have written down what was the negative curvature model. So a metric on R2n plus 1 over the form, I'm considering this kind of metric here. So here there are many experts on contact metric. So I say that this is not contact metric because you see dz here. Actually, it has to be dz minus y dx or something, right? So so this is not contact metric, but this is close to such a contact metric, actually. So if you think of a dz, so n equals 2n plus 1 equals 3 dimension, then you have a y dx square term plus dx square plus dy square. So that's the standard metric, standard contact metric. And if you multiply by c square g, then you may think, well, that if you multiply c square only, then it's not contact again. But after I did some deformation, I will multiply that I will multiply 1 over c square, and then I'll go back. So if I multiply c square g, then you will have a cz coming in, and then you think the dx cx equal capital X, cy equal capital Y, cz equal capital Z. Then with respect to this one, and you get dz minus y dx squared, but here you divide by c, and then you get dx squared plus dy squared, right? And if c is big, then this is close to close to Euclidean metric. Actually, this has the scalar curvature 1 over c squared, and this has scalar curvature minus 1. Scalar curvature. That's the scalar curvature. So the reason why I'm thinking of this one is that if we put f here and here, then multiplying this effect will be reflected back in here. This one is a contact metric, actually. So this one is a contact metric, and then what I'm saying is I'm thinking of C very big, and I'm thinking of a ball, coordinate ball on x square plus y square plus z square. So I have attention to this space. So this is capital X, Y, Z. And if C is very big, then it's close to this shape, close to this metric. Sorry, I didn't. Yeah, this polar coordinate. Polar coordinate change. I didn't mention that. But instead of this dx dy, if I put the dr, rd theta, that will be the same as this one. So I know I should write down here, instead of this one, I should write down something like this one in here. But to make it simplify, I just wrote down this one here. And then this metric, the scalar curvature can be computed in this one, in this way. And if you look at this one, this is positive and this is positive. So if you can make this 0 inside, then you can get metric like this. Fi will be identically equal to 1 here, but inside it won't be constant and it will vary, but it makes this 0. Then you get this thing. So if this matrix has such a one, then the corresponding contact matrix will be close to this one. So it's not Euclidean, but it's close to Euclidean, actually. So now, for expansion of the negative curvature, so this part is the core. It entails a long formula and estimation, and it's not easy to explain in quickly. But so if I have the general expansion scheme is this one. If you have a contact matrix, then I will express this one in local coframe like this. So omega I is a local coframe. So if omega I is, of course, omega 2m plus, the last omega 2m plus 1 will be the contact form like. And if I choose omega I geometrically efficiently, then there is a chance that I can do the following estimation work. So given so here what I have written down is just this one. If we have matrix like this, then I'm going to deform it to this shape, because this will, if this is a contact, then this will be contact. So actually this omega 1, omega 2, omega 3, I didn't explain what they are, but it's reflecting the contact structure, so that if this is contact, then this is contact with respect to the same eta. So F will have a spot in a ball. So then what I'm interested in is this difference of scalar curvature. And then the difference will be explained in this way. Here F is here. So this sub index 1, 1, 2, 2, 2, and so on. These things are the first order derivatives. And if we have two double indexes, then it's second order derivatives. Yeah. Okay. So here you see Aij case, then it's coming from the curvature one forms of the metric G. And here you see Q. Q is Q consists of Aij case. So it's a quadratic form of Aij case. So it looks a little complicated, but so I cannot do much. I cannot show the detail about that. But what I needed was this: the difference of these two scalar curvature was satisfies these three. So if you so what was the point I was explaining? So I spread many balls, and I'm expanding the negativity. So let's say I have finished one step, okay, and then I'm going to do next step. So the previous step, the result of the previous step was G, with G, and the G tilde will be the next step matrix. So between G and the G tilde, I have to do some control. Right? If I can do it, then everything works. Right? So this difference it matters to us. So if I made SG negative, and if we have this relation, then SG tilde will be negative, because SG was negative by induction hypothesis. And again, yeah, this so outside the large ball, I don't change it. So what is the small ball, large ball? So it's the same the picture. Small ball was this one, large ball is this one. So here C and C epsilon is okay, both are constants, but epsilon is C is C is kind of bigger constant than epsilon. So epsilon is pretty small. So in the annulus means large ball minus the complement of a small ball in large ball. So the annulus is this part and this part. Of course, this is not one-dimensional, so it's annulus-like region. So on that annulus-like region, I cannot have such one, but we have a very tiny minus epsilon because I'm spreading out. So if you look at this part, then it will be what you can expect is minus epsilon. But inside the small ball, you have we had a pretty negative at first, so you can have minus C. So this 1, 2, 3 steps is the core of the argument. So that was done to deal with all these terms. So if we are if we are done with this one, then then we can I guess I don't have to do it again, but then after number 1 ball spreading, when I do number 2 ball spreading, I think of this difference SG tilde minus SG was okay, and then number 3 balls okay, and so on. Then you can finish it, all these estimates. So okay. Yes, my time is already done, so I will just finish without problems. So, here the first open problem is 3 dimension is missing yet. So it will be good if one can finish this 3-dimensional, so that you can make a full statement. And second is the space of almost scalar matrix or contact matrix with a negative scalar curvature on a manifold. So you think of this infinite dimensional space, connected or contractible. This question is influenced by Rokamp because he proved that the space of Riemannian matrix with a negative scalar curvature is contractible. So this kind of thing may contain some topological information about it, which to identify what it is difficult, but I'm just proposing. Does every symplectic or contact manifold that dimension equal to 3 admit an almost scalar matrix with a negative ridge curvature? Rokamp asked me to do this, but he said I have to use 3 functions. I got fed up with the 2 functions. The 2 functions was already too hard to do, and he mentioned 3 functions. So I thought, so for now that's all.